All right. Hello. I'm going to run through these day 8 notes. I'm going to go as pretty quickly, so feel free to pause, fast forward, rewind, put me on like 2 or 3 times faster, whatever you need to do. But today's really just about deductive reasoning and writing a whole bunch of sentences. So it doesn't really involve any math per se. Just get your writing hand ready. So, all right. So the first thing we're going to talk about is deductive reasoning. We did inductive reasoning last time, and inductive reasoning is when you find patterns, but deductive reasoning is when you use previously learned information to make an argument about what you can conclude comes next. Okay, so when we start doing our geometric proofs are all about deductive reasoning, and we've already started talking about this a little bit in class. So you can only use facts though. So for us, that would be definitions, properties, postulates, we've learned some of those already, theorems, and laws of logic. And some of those are what we're going to be talking about today. Okay, so what we're going to do today is write a bunch of sentences, and these sentences are special because they are called conditional statements. Okay, a conditional statement is an if-then statement. Okay, the first part is the hypothesis. That is the statement that follows the if, and then the conclusion is the part that follows the then. The conclusion is what must be true if the hypothesis is true. And we always assume the hypothesis to be true, or else why would we say it? Okay. Our world pretty much runs on if-then statements, and whether we know it or not, like advertising for companies like, if you use our toothpaste, then your teeth will be brighter, right? And so a lot of the stuff we buy and that is advertised in the real world kind of runs off of this premise. Okay, so here we go. We're just going to talk about an if-then conditional statement. This one that says, if a quadrilateral is a parallelogram, then it is a square. All right, so the first thing we're going to do is underline the hypothesis. Well, the hypothesis is the sentence that follows the if. It does not include the if. Right? The if stands alone, and then the hypothesis is the statement after that. So a quadrilateral is a parallelogram. So what we know for sure is no matter what we're looking at, we know we are looking at a parallelogram. Okay? Then the conclusion, it is a square. It tells us to underline that twice. Of course, I did connect it. And so it's up to you to figure out what the truth value, which I will label TV, is that truth value true or is that false? Okay, so if it's true, it has to be true 100% of the time, all the time. And if it's false, then you must be able to provide a counterexample to prove why it's false. So I know most of you guys are already thinking, I'm hoping that this one is indeed false. And of course, the reason it's false is because, yeah, I could be looking at a parallelogram, but that doesn't mean it has to be a square, right? So this is a parallelogram, but not a square. Or we could have a rhombus, right? Which has all congruent sides, but is still not a square, right? Or we could have a rectangle, which is also a parallelogram, but not a square, right? And so obviously you don't have to draw all 3 of these, right? But this would be an example of a counterexample that would prove that this conditional statement was false. Okay. All right. The next thing we're going to do is practice writing some if-then sentences. A lot of statements that don't read as actual if-then statements can be rewritten as if-then sentences. So that's what we're going to do. So the first sentence is, I decorate a tree for Christmas. All right. And so a lot of people want to write something like, if I decorate a tree, then it is Christmas. But then we want to think about if that's 100% true, right? Of what the context of this sentence is saying. So technically, if I wrote, if I decorate a tree, then it is Christmas, that's a little misleading because some people decorate trees for a lot of reasons other than Christmas time, right? So some people might maybe decorate, they have like egg trees for Easter, or they put ghosts in their trees outside and decorate them for Halloween, right? And so people might decorate trees for a lot of other reasons other than Christmas. So when we write an if-then statement, we want to make sure that it's actually a true one and is, what's the word I'm looking for? is saying the same thing that the sentence is. So if I was to write a sentence, I would write, if it is Christmas, then I decorate a tree. Right? And now we're kind of giving that same connotation as the original sentence. Now, there is one thing that I did in this sentence that I shouldn't have. I really, really, really want us to try to stay away from the word it. I naturally just did that here because it just kind of flows with if it is Christmas. Technically, you want to always stay away from the word it. So maybe I should write if the season is Christmas, or if the holiday is Christmas, or something like that. Even though that kind of sounds weird, we just want to always stay away from that word it because you haven't really described what it is yet, right, as the subject matter. So just be cautious there. All right, the next sentence is a square has 4 congruent sides. Well, that, of course, is a true statement. So if I want to write it as a conditional statement, I might write something like, if a shape, again, I'm trying to stay away from the word it, if a shape is a square, then, put my comma, you can use it in the second half because, of course, you've already defined your subject in the hypothesis. Then it has 4 congruent sides. I'm going to abbreviate a little bit if everyone's okay with that. Okay, so just a little practice writing if-then sentences. All right, turn the page with me. These are what we call logic statements. There's actually an entire branch of mathematics devoted to just logic math. So we're just going to touch on a little bit of that today. So a conditional statement is the original if-then. That's what we've been talking about. If you were taking a logic class, like in college, they often like to use P's and Q's to represent the hypothesis and conclusion, just as a shorthand way instead of having to say hypothesis and conclusion all the time because they're kind of long words. So our original conditional, we would say it's if P, then Q, where P is the original hypothesis and Q is the original conclusion. Okay, so I'm going to kind of use the P's and Q's to make sense of the other 3 types of statements that we can write based on the original conditional. Okay, so the next type of logic statement we can write is called a converse statement. Now, I know this is going to sound super cheesy, but a way that help you remember what a converse statement is, I don't know about you, but the first thing I think of when I hear the word converse is I think of shoes. And maybe when I think of shoes, I might think of flip-flops. I know that's a stretch, but just run with me here. So converse statement is when you flip-flop the original hypothesis and conclusion. Okay, so they just switch places, right? And so I like to remember that with flip-flop. Flip-flops are shoes. Converse are shoes, so that's kind of how I help myself remember that. So we flip-flop the original hypothesis and conclusion. So if the original conditional statement is if P then Q, then my converse statement would be if Q then P. Okay, so we just take the statements and we reverse them. All right, so here we go. Let's go look at an example of a converse, or we're going to write a converse. So the original conditional here is if a triangle is a right triangle, then it contains one 90-degree angle. And then you'll notice over here, I'm asking for the truth value. Well, of course that's true. That's literally the definition of a right triangle, is that it contains one 90-degree angle. But now what we're going to do is we are going to flip-flop it, right, and write the converse of this conditional. Now, the one thing you do want to be careful about is I don't want to just pick up the conclusion and just move it to the front, because my conclusion contains the word it, which I don't want in the hypothesis. So we want to make sure we find that subject, which would be a triangle, right? And I'm going to keep him in the front as my subject because my reader needs to know what we're talking about. So here we go. If a triangle, but now I'm going to write the conclusion, contains one 90-degree angle, then now I can use the word it. is a right triangle. And then, of course, what we're asking now with this truth value is it still true even though I flip-flopped the hypothesis and the conclusion? And in this case, yes, it is still true, right? A triangle that contains one 90-degree angle is, in fact, still a right triangle, right? Now, this is a special type of converse. If you look at the little box here, with the blue highlighter. This is a special type of converse. It is not always true that when you flip-flop the conditional, that the converse is also true. They actually very rarely share the same truth value, right? But these two statements happen to be true no matter whether you say them forwards or backwards. And that is a special type of statement. And that means we can actually write them as a biconditional statement. And we're going to see a lot of biconditional statements in this class. They're mostly written as theorems. And biconditional statements are not actually if-then statements. They are if and only if statements. So it would look like this. P, if and only if Q. P, if and only if Q. Now, basically what that means is the statement is true forwards and backwards. So it doesn't matter if you put the P first or the Q second or vice versa, right? It's the statement is true either direction, okay? So in this case, I can write these statements as a biconditional because they were both true. And it, like I said just a second ago, it doesn't matter which one you say first or which one you say second because it's true forwards and backwards. So I might write something like this. A triangle is a right triangle. Sorry, I'm going to zoom up a little bit. If and only if it contains one 90-degree angle. Okay, so here's that if and only if. And of course, I could have written this in the opposite. I could have said a triangle contains one 90-degree angle if and only if it is a right triangle, right? So any direction is totally fine. All right, there's two more statements that we need to learn. The next one is an inverse statement. Well, I don't know if you remember about inverse statements, right? But inverse statement means like the opposite, meaning like addition is the inverse of subtraction, right? Division is the inverse of multiplication, right? They're opposites, right? And so that's what the inverse statement is, right? It's the opposite meaning. So usually that means like if I said, I like ice cream, well, the inverse of that would be I do not like ice cream, right? And so you are just saying the opposite meaning. Now you do want to stay away from words like, if I said I love ice cream, I wouldn't want the inverse to be I hate ice cream because the words love and hate are very subjective to people. And there's a lot of levels, in there. So if you said I love ice cream, then you would just want to say, well, I do not love ice cream as the inverse, right? So usually we're putting the word not in or we're taking the word not out. Okay, so if I said I do not like cats, the inverse would be I do like cats. Okay, so that's literally all we're going to do. But it's the original conditional that we are inverting, okay? And we also like to use the word, and you need to know this, negate, right? Which means to make negative connotation, right? So adding the word not. So we're going to negate the original hypothesis and conclusion. Okay, to negate, right? To give the negative or the opposite meaning, right? Like I said, usually that means using the word not or taking the word not out. So if my original conditional is if P then Q, then my inverse would be if not P, then not Q. If not P, then not Q. Okay, same order as the original, just the opposite meaning for the hypothesis and conclusion. And then, of course, your job would be to read that and determine if it was still true or if it was now false. We're going to do that in just a few minutes. All right, the contrapositive is if the inverse and converse have a baby, and it's both, right? So the contrapositive is where we flip-flop and negate the original hypothesis and conclusion. I am going to run out of room here. So I'm just going to abbreviate if that's cool with everybody. So we're going to do both. We're going to flip-flop and negate the original hypothesis and conclusion. Okay, so again, if the original conditional statement was if P then Q, then my contrapositive is going to be if not Q, then not P. Right? We're flip-flopping and negating. And then, of course, up to you to determine if that still is a true or a false statement, which can get kind of weird sometimes because when you start throwing like knots in there, and it can get kind of weird. So we'll talk more about that in just a sec. Okay, so if you turn the page, we are going to do one full example of this and then just talk about a couple more quick things and we'll be done. All right, so we're going to use this conditional statement. If it is raining, then the ground is wet. Now, of course, I did a big no-no here. I used the word it in the hypothesis, which of course I shouldn't, but we're going to let it slide this one time, right? I could have said like if the weather is raining or something like that, but that just kind of sounds weird. So if it's raining, then the ground is wet. Now you do want to take these statements with a grain of salt, meaning please don't add other variables to the mix here, right? You can't say, well, what if I'm standing under a gazebo, or what if I'm like, you can't play the what if game. Like you just have to take the statements for face value of what they are, right? So if it's raining outside, is the ground getting wet? Yes. Right? So if it's raining, the ground is wet. That is a true statement overall, right? You can't add any other variables or any other weird parts of the story or anything like that. Just in general, yes, that is true. Okay. Now we're going to write the converse of that statement. Well, remember the converse is the flip-flop. So here we go. If the ground is wet, then it is raining. So this is a great example of flip-flopping the statement and then seeing whether that is still true. And I want you to think about for that a second, right? If the ground is wet outside, does that mean that it is raining? And no, right? That's a false statement because there's a lot of reasons why the ground could be wet, right? There are sprinklers on. I spilled my water on the ground. There was a water balloon fight, right? People are splashing water out of a pool, right? I spit on the ground, right? There are a million reasons why the ground can be wet, but it's not actually raining outside. So this is a great example of the conditional being true, but as soon as you flip-flop it, not so much, okay? All right, now we're gonna write the inverse. Now here's the trickiest part. Please make sure you're not writing the inverse of the converse, right? We want to write everything goes back to the original conditional statement. So remember the inverse is negating the original hypothesis and conclusion just in the order it was at the beginning. So in this case, we're going to give it the negative meaning. So instead of if it is raining, we'll say if it is not raining, then the ground is not wet. If it is not raining, then the ground is not wet. So sometimes you got to think about these a little bit. So if it's not raining, so okay, well, there could be like all those examples that I just said a second ago. Water balloon fight, pouring my drink out on the sidewalk, sprinklers going off. That's not rain. Then the ground is not wet. Well, that's also false, right? Because the ground can be wet even though it's not raining. Okay, so taking the inverse of that conditional, also false. All right, and then lastly, we're going to write the contrapositive. But remember, again, We're going all the way back to the original statement. Make sure you don't use one of the previously written ones that we have written down. So now with the contrapositive, we are going to flip and negate. Okay, so here we go. If, let's see, now we're going to flip. So it's going to be the ground is wet, but we're going to negate it. So if the ground is not wet, then it is not raining. If the ground is not wet, then it is not raining. Okay, so think about that for a second. The ground is not wet, so the ground is dry. So if the ground is dry, then it's not raining outside. Well, that's true. Okay. Again, sometimes you got to think about it a little bit, all right, and figure out what that's saying. All right, our next question is, can we write this original conditional? Would we be able to write it as a biconditional? So if you remember up here in the box, the only way to be able to write a biconditional is if the conditional and the converse are both true, right? So if we go back here, clearly that is not true in this particular statement, right? And so no, we cannot write the biconditional because the converse, I'll just say the converse is false. The converse is false. And you can also write a couple of other things. You could say that the conditional and the converse don't have the same truth value. The conditional and the converse are not both true. But since the conditional was true and it was just the converse that wasn't, then I'm just going to use that as my reason. All right. Now, if you're one of those people and you're still kind of like stuck on this true false, like I do not understand why some of those are true false, I'm going to give you a little helpful hint. Whenever you do conditional statements or logic statements, the converse and the inverse will always have the same truth value, always. So usually most people have a pretty good handle on the converse, but that inverse where you start throwing knots in there, it can really get confusing. So if it helps you out, the inverse will always have the same truth value as the converse. And I'm sure you probably picked up on this, the biconditional, the contrapositive and the original conditional will also always have the same truth value. Okay, so if you ever get stuck on that contrapositive and whether it's true or false, you can always go back up and look at what you wrote for the conditional, and it should be the same. Okay, so they can either all four be true, they can all four be false, or it's going to be true, false, false, true, or false, true, true, false, right? So those are like the four different truth value scenarios that you would be seeing. So it's just like a little, checkpoints just in case you need it. All right, let's talk about the vertical angles theorem really quick. It's really the only theorem we've learned so far, and I went ahead and wrote it again. It says if two angles are vertical, then they are congruent. Notice it's written as an if-then conditional, as almost every theorem that we learn will be written as an if-then. So if two angles are vertical, then they are congruent. Can that be written as a biconditional? So think about that for a second. So I'm going to write, well, of course we know this is true, right? We know all vertical angles are congruent. But what if I wrote the converse of this theorem? The converse would say, remember converse is flip-flop, if two angles, I'm going to abbreviate, if two angles are congruent, then they are vertical. This is what the converse statement would be. Right? And so the question you have to ask yourself, well, is that true or false, that statement? If two angles are congruent, then they are vertical. And I'm really hoping you're screaming at your iPad, false, right? Because I can draw lots of congruent angles, right? Let's say I have a picture that looks like this, and I have an angle bisector. Well, I have two congruent angles. Does that mean that they're vertical angles? Well, clearly not, right? Because vertical angles are opposite angles created by intersecting lines, and that's not what's happening here, right? So the vertical angles theorem is not written as a biconditional because it's not true when you read it in reverse, okay? All right, guys, that's pretty much it for today's lesson. I'm going to breeze through this little part here. This is kind of a little extra about parallel and perpendicular lines, just to make sure that we're all clear with our symbols and stuff. So we've already talked about that first symbol. This is now the third time we've seen it, so I just want to make sure, right? So we would say, we know that that little upside down T, it means perpendicular. And here's the formal definition of perpendicular, right? Two lines that intersect to form right angles. Right, and so we would be looking for that little right angle box and all that good stuff. And if I label this L and M, we did this before, right? We would say L is perpendicular to M, right? That would be our notation there. What we haven't talked about yet, but we will be getting into a lot in Unit 2, is parallel lines. And parallel lines, this is the symbol for parallel. You can just draw two little side-by-side vertical lines, or you can tilt them. That's totally up to you, right? So this symbol means parallel. And you guys know what parallel lines are, right? Parallel lines are lines that will never cross. Right? They exist in the same plane, but they don't ever cross one another. So if I labeled this A and this B, right, I would say A is parallel to B, or you can do little tilty, slanted diagonal lines. I always make mine vertical, but it doesn't really matter. Now we do need to talk about some notations on our diagrams. Like we know here, oops, sorry, I was trying to get a highlighter. We know with perpendicular, we're looking for the little right angle box to tell us that things are perpendicular. Well, we need the same thing with parallel lines. Parallel lines also need some form of notation on them to tell you that they're parallel. And so what we look for with parallel lines is we look for a matching little number of arrows on the lines. So if you see little solid arrows on the lines that look parallel, that's our notation for that. If you have multiple parallel lines, well, then you put another little set of arrows, right? So it's kind of like congruency marks, right? You match up the number of arrows. So that's kind of what that looks like. Okay, lastly, these are little conditional if-then statements that make you go, I wonder if that's true all the time or not. So I'm going to fly through this pretty quick. The first one is pretty easy. It says if M is parallel to N and N is parallel to K, then what conclusion do you think can be made? All right, well, I'm going to draw a little picture of that. So M, some line M, is parallel to some line N. And I'm going to put my little arrows on there to show that. But it also says, and N is parallel to K. All right. So I've got a third line. He's labeled K, and he's also parallel to N. So we're going to have another arrow. So what conclusion do you think they're trying to get us or trying to lead us to? Well, hopefully you're catching on that since everybody's parallel to N, then everybody's parallel to each other. So they're trying to get us to conclude that then M must be parallel to K. And they're asking, is this always true? Right? In every physical realm that you can possibly think of, is this true? And we'll come back to talk about this in just a few minutes more. But the answer here is yes. That is always true. If two lines are parallel to a third line, then those first two lines will always be parallel to one another. Okay? Again, we're going to come back to that one in just 1 second. I want to talk about this guy. This one is kind of the same premise, except it is with perpendicularity. All right, so again, I'm going to draw the picture. This one says A is perpendicular to B. Okay, so I'm just going to eyeball it. There we go. We're going to make this A, and I'm going to make this line B. There we go. So I've drawn A is perpendicular to B, but then B is also perpendicular to C. Okay. So let's see, I've got another line here, C, that is also perpendicular to B. So I'm hoping after drawing that out, you're kind of seeing the conclusion that they're trying to get us to here. And they're trying to get us to make a connection between A and C. Well, if A and C are both perpendicular to B, and they're both hitting B at that 90-degree angle, then of course that means that A must be parallel to C. They're running at the exact same angle, hitting line B, so they must be parallel to each other. And I don't want to really draw this out anymore, so I'm just going to kind of go forward with it. The question is this always true? Right? And in that case, I'm going to say no, or I'm going to actually say sometimes. Right? If this was an always, sometimes, never question, this would be a sometimes answer. And this would be the yes part of it. Right? Because obviously we drew this line, so we know it works. But this is yes. And the reason why it's yes is because I drew it in 2 dimensions. Right? This is just a 2-dimensional drawing of 3 lines intersecting. No big deal. Yes, it's always true if I'm in 2D. But we can't just always think in 2D. We always have to think in 3 dimensions as well and ask ourselves if it's still true then. So what I'm going to do is I'm going to draw a prism, very much like we did in the first couple of days of notes, right? To look at a 3-dimensional space. A prism is an excellent way to look at 3 dimensions. And I'm just going to pick 3 lines in this diagram that could also be representing this hypothesis, okay? I'm going to highlight them as I go. So it says if A is perpendicular to B, okay? So let's say this is A and it's perpendicular to B. So I'll just make this B. You can pick any line in the figure as long as it's perpendicular. And that definitely, if this is a rectangular prism, which it is, that's my goal, right? Then yes, they are perpendicular. So I've got that. I've got A perpendicular to B, but then I'm going to go in and do, I'm going to find another line that's also perpendicular to B. I'm going to pick this guy right here, and he would be C. And then you have to ask yourself, well, in 2-dimensional space, we found out that A and C were parallel, and that was our conclusion. But in 3-dimensional space, are A and C parallel? And no, right? They're actually perpendicular to each other as well, right? In that corner. So this would be an example of no, right? Not in 3D, right? So sometimes there's conclusions we can make, but you have to you've got to think about it in each type of space. Okay. I know it's kind of weird, but it's a great way to kind of analyze those sometimes statements, you know, when you have to come up with a counterexample. Sorry, I was going to try to minimize this a little bit. There we go. It's large. Okay. Just for funsies, if I went over here and analyzed this number 1, the one on the left, if I made a 3D rendition of that one over there, I didn't want to talk about it yet over there. But if I did the exact same thing on this side, if I found a line M that was parallel to line N, okay, so let me pick different color. There we go. So let's say this is M and this is N. And then I go pick a line that is also parallel to N and make it K. Well, all right. Let's see. This line is also parallel to N, so I'll call him K. And you'll notice he is also parallel to M, right? And so for the laws of parallelism, as they would call it, it doesn't matter whether you're in 2D or 3D space. But with the laws of perpendicularity, it does. Okay, so just kind of some if-then sentences to kind of make you think outside the box just a little bit. Okay? All right, I hope you have a lot of fun writing sentences today. That's pretty much all you're doing on your homework. Again, when you're writing your sentences and determining whether they are true or false, please don't think too much about them. Just take them for what they are. If you don't agree with my true or false and you have a rebuttal, that's perfectly fine. Okay. All right. We will go over any questions that you have tomorrow, and I hope you guys have a great day.